Alright, I'm going to go over the study guide like I said I would. Make sure you pay attention to the part about moles, which is going to be mostly the whole thing. So, this is your last chance to improve your grade. Watch this as many times as it takes to get good at this stuff. Let's go. Okay, so the first thing we got to do is balance this equation. Okay, this equation has chemical formulas that represent the molecules involved in the equation. This side is the reactants, this side is the products. That arrow tells us that there's a reaction taking place. Remember, the first thing we do is we take an inventory of the atoms on each side. Remember, these subscripts, they tell us how many of each element there are in each of these molecules. When we add the big number, the coefficient in the front, that's going to tell us how many molecules there are. Remember, this C2H6 represents a molecule, all right, which is several atoms bonded together. Okay, so let's get started doing our inventory. This side we got 2 carbons, 6 hydrogen, 2 oxygen. This side we got 1 carbon, we got 2 hydrogen, and we got 3 oxygen. Okay, now this is a really hard balancing equation. Okay, I'm sorry, but it's a hard one. Okay, I want you guys to struggle with this. I know you're going to, because you got to do a lot of back and forth with this one. If you haven't done this yet, please turn off the video and just try to hammer it out on your own, because you'll learn a lot through struggling, believe me. Okay, but if you've already done it, or if you just are totally stumped and you're giving up, you can see how I do it. But there's really no method to it besides struggling. Just go through the trial and error. Okay, so I think what I'm gonna try to do first is work with these hydrogens. I don't know why, I just think that's gonna be the way to go. So let's put a 3 right here, okay? Because that'll change that hydrogen to 6, which is what we want. Okay, but at the same time, it changes our number of oxygens from 2 to 3, 4, 5. And that's not exactly good, okay, because we have 2 on that side. Okay, so let's go ahead. We know that we need to change this carbon too. So let's go ahead and put a 2 right there too and change that right now. And when we change that, because there's an oxygen in this molecule, that's going to change the oxygens too. And it's going to add 2 more oxygens. So that's going to change this to a 7. Okay. So already we kind of got an issue, because we can't multiply this by anything to make 7. So we already know we're gonna have to do like a common denominator. One thing that's cool is that we can, if we change this to a 4, because we have a loner oxygen on this side, we can change this odd number to an 8, which is what we're gonna try next. So keep an eye on if you have an odd number of if you're trying to make this an even number, so you can make that 2 fit into it. Change this. If we change this to a 4, we just added another. We just changed that to an 8, but at the same time we changed this hydrogen to an 8. Okay, and that's kind of a problem, because now we gotta do something about this 6 not matching this 8. So what do you think we should do? What do you think we should do? Well, we're gonna have to, we know we're gonna have to need more on this side. So let's put a 2 right there, okay? Because we know we need more hydrogens on this side. So let's just go with the smallest coefficient we can do. That makes this 12, and it changes this to 4, okay? So let's adjust our carbon over here. Let's change this to a 4, because we know we gotta do that. And that fixes this, but now we got 1, 2, 3, 4, 5, 6, 7, 8. Oh, excuse me, we got 8, 9, 10, 11, 12 oxygens on this side. Okay, we got, oh yeah, don't forget that when we double this, we gotta double all the elements in there. So this looks good. 4 carbons, 12 hydrogens. Okay, so we need more hydrogens on this side. We need, what is it, 4 more hydrogens on this side. So let's change that to a 6. Because now that's gonna change this to a 12, which is what we want. But it's also gonna change our oxygens. So now we got 8 plus 6 equals 14. Oh, you know what? I think we can do it now. Let's double check. 2 times 4 goes 8, 9, 10, 11, 12, 13, 14. Okay, good, because yeah, we can multiply 2 by something to get 14. And that is 7. So 2 times 7 is 14. Guess what? We did it. We got 4 carbons on this side, 4 carbons on that side, 12 hydrogens, 14. Okay, so yeah, a little bit trickier. We had to do a little bit more guess and check and crossing out, but we did it. Okay, you can do it. Just be persistent. All right, you can do it. Okay, so that's balancing the equation. So now we got that balance. We can erase this. And move on. Okay, so the next part of this study guide has this question right here. It says, if 2 grams of H2O is produced by this reaction, how many grams of C2H6 did you start with? Okay, and we can do that by using moles. Okay, so we know we got 2 grams of H2O, and we know that for every 6 molecules of H2O, because remember that coefficient tells us how many molecules, we know that for every 6 molecules of H2O, we needed 2 molecules of C2H6. Okay, so let's take our 2 grams. First thing we need to do is we need to find out what the molar mass of H2O. We need to figure out what the molar mass of H2O is. And that's pretty easy, okay? Because if you look on the periodic table, hydrogen has a molar mass, or atomic mass of 1.008, okay? And it's got 1 proton, okay? And then oxygen has a molar mass, or an atomic weight of 15.999, okay? And it's got 8 protons. Okay, so if we calculate the molar mass, remember the molar mass is the mass when you have 1 mole. Okay, 1 mole equals 6.022 times 10 to the 23. Okay, so when you have 1 mole, you have this many molecules. Okay, and the mole, this special number, is nice because that's when the atomic weight matches the actual weight in grams, the mass in grams, when you weigh the sample on a scale. Okay, so if we got 2 hydrogens, we got 2 times 1.008, okay, plus 1 times 15.999. And you can round these, okay? You don't need to do this decimal, it's all right, just round it. So the molar mass, first off, the atomic weight of 1 H2O molecule is 18 AMUs, okay, atomic mass units, okay? But when you have a whole mole of those molecules, the weight in grams is equal to the atomic weight in AMUs. So the molar mass is 18 grams, okay? Now, do we have a mole? No, we have 2 grams of H2O. So we have less than a mole, okay? We know that it takes 9 times what we got to make a mole. Okay, so we basically have 1/9 of a mole, because 2 grams is a lot less than 18 grams, which is the molar mass. Okay, so we have 2 grams of H2O equals 2 divided by 18. It's just like eating a pizza. If you cut a pizza into 4 slices and you eat 1 slice, you eat 1/4 or 0.25 pizzas. Okay, you didn't eat the whole pizza. You ate 1 slice of the 4 slices, 1/4, 0.25 pizzas. So this is the same thing. We don't have a whole mole of H2O. We don't have a whole 18 grams. We have 2 grams. Okay, so 2 divided by 18 equals 0.11. So this is, let's just round it to 0.1. Okay, we got 0.1 moles. Okay, so this is 0.1 moles. Okay, not because of the 6, but because we have 2 grams. Okay, this 6 tells us basically a ratio. They call this a stoichiometric ratio. It tells us that we have 3 times as much water as we do C2H6. Okay, so that means we're going to divide that 0.1 by 3. And we get 0.03. Because that is 1/3, because 2/6, you have 2 of these for every 6 of these. That's 2/6 or 1/3. Okay, so you're going to divide this by 3 to know how many moles of this we got. Okay, so now we got to figure out, because it asks how many grams of C2H6. Okay, so now we got to convert that to grams. Okay, so basically 0.03 moles of C2H6 equals how many grams? And the first thing we got to do for this is find out what the molar mass of C2H6 is. Okay, and once again, we go back to the periodic table. Okay, we already know how much hydrogens are worth. So if you look at the periodic table, carbon looks something like 6 protons, and then it has a molecular mass of, I think it's around 12.011, something like that. I forget exactly, but I know it's about 12. Okay, so if we have 2 carbons, that's 24 plus 6 hydrogens. What's 24 plus 6? Okay, it's equals to 30. Okay, 30 grams. Okay, so 1 mole of C2H6 is 30 grams, but we don't got 1 mole. We got 0.03 moles. Okay, so the way we solve this is we go 0.03 times 30. And the reason why we multiply is because if you were like, okay, how do we do this? Okay, because let's think about something simpler. Let's say 0.5. Like if there's 20 kids in the classroom and half of those kids like Nickelback, how many kids in the classroom like Nickelback? You would do 0.5 which is the decimal equivalent of 1/2, you do 0.5 times 20, and 0.5 times 20 equals 10. 10 kids like Nickelback. So this is the same type of math. You do the decimal times the total, and we know the 0.03 times 30 is 0.9. Okay, so 0.9 of these molecules like Nickelback. Just kidding. All of them like Nickelback, because Nickelback's the best band ever. Okay, so this is equal to 0.9 grams. Okay? 0.9 grams. Because the molar mass is 30 grams, but we don't have a mole, we got 0.03 moles. Okay, so we got 0.9 grams. Okay? Now let's take a look at this. If you want to know how many moles of O2 you had, we would do 7 divided by 2. 7's 3.5 times 2. So there's 3.5 times more moles of this than there is this. So 3.5 times 0.03 equals 0.105 moles. Okay, and for this, you know that 4 is 2 times that. So we know that this is just 2 times whatever this moles is. So this one is 0.06 moles. Okay, so we can figure everything out. If we know the mass of one of these and we balance our equation, we figure out the mass of the rest. Not that difficult, you just gotta learn the process. All right, let's move on to the second part of the first page of the study guide, which maybe is a little bit harder. I don't know, not really. It deals with energy. Okay, it deals with the change in energy. Okay, because remember when you bonds form, molecules form in the first place because they form bonds because that stabilizes them, because they like to have octets, and so they share or lose electrons, so that they have the completed valence shells, which they like, you know. Okay, so there's energy involved, because remember, stability is associated with energy. Okay, we'll talk more about that in a little bit, but let's get into this. Okay, so it's basically asking you like how many it's basically asking you how many joules does it take to break up all of these molecules. Okay, so first thing we gotta do is the energy is in terms of bonds, the strength it takes to break the bonds, which is given by the table. So it's nice to draw the molecules so you know what bonds are involved. Okay, so C2H6. Remember, you know carbon forms 4 bonds because it's 4 electrons away from having an octet. It's a non-metal, so it's going to form covalent bonds. Okay, and you know that hydrogen forms 1 bond because it's 1 bond away from having an octet. It's 1 electron away from having an octet. Okay, so that molecule looks like that. Okay, we put a lot of time into drawing molecules. Okay, we don't need to draw the 2. We know we got 2 of them, but I don't have a lot of space right here, so we'll just multiply whatever we calculate for the bonds we got by 2 when we get there. Okay, we know we put a lot of time into oxygen. You know oxygen forms 2 bonds because it's 2 electrons away from an octet. Oxygen looks like this. Okay, we got 7 of those bad boys. So whatever the energy it takes to break this up, you have to multiply that by 7. Carbon dioxide looks like this. Because remember, carbon forms 4 bonds. It doesn't need to be bonds between different elements. They can do double bonds between one other element. So a double bond, the 2 double bonds counts as 4. Okay? And we got H2O. Hopefully you're pretty familiar with H2O by now. Okay? H2O looks like that. Okay, so we look on the table and the CH bond is 411. Okay, so 411 times 4, And that is, oh, excuse me, we got 6 of these bad boys. Times 6, 2,466. Okay, now this is very important. If you look at the units on top of these bond energies, the units is in kilojoules per mole, kilojoules per mole, because there's the J, you know, that's joules, that's what we measure energy in, is joules. The K means 1,000. Okay, so this is kilojoules per mole. Now, do we have a mole? No, we don't. Okay, no, we do not. Okay. Oh yeah, before I said that we're gonna have to multiply this by whatever that coefficient is, I forgot we don't have to multiply it by the coefficient, we multiply it by the moles. Okay, because moles is better, okay, because that moles tells us exactly how many molecules we got. Okay, so we need to so this is, if this is 2,466 kilojoules per mole, then we need to factor in how many moles we actually have. And we don't have a mole. We have 0.03 moles. Okay, so it's going to be the amount of energy it takes to break up how many C2H6 molecules we got is actually going to be less than this. Okay, so it's the same math as before. It's the Nickelback math. Okay, so we're going to do 0.03 times 2,466, and that's going to be less. And the answer is 73.98. Let's just round that to 74, okay? Close enough. Okay, so that's 74 kilojoules. 74 kilojoules to break that up, okay? Because it's 2,466 per mole. We don't got a mole, we got 0.03 moles. So 74 kilojoules. Okay, let's do the oxygen double bond now. Okay, this, according to our table, is worth 494 kilojoules per mole. Okay, but we don't got a mole. We got 0.105 moles. So 0.105 times 494 equals 0.105 times 494 equals 51.9 kilojoules. Okay, 51.9 kilojoules to break up the amount of moles that we got. Okay, so let's add this to this. And that is 125.9 kilojoules. Okay, so to break all the bonds, because in order to do this reaction, we gotta break all the bonds on this side and reform these atoms and transform them into the bonds on this side. So to break all the bonds on this side takes 125.9 kilojoules of energy. Okay, that's a decent amount. All right, so let's go over here to this side. Okay, so the C double O bond is 749. Okay, and we have 2 of them in this molecule. We got 2 of them in this molecule. Equals 1,498. Okay, kilojoules per mole. Okay, but we don't have a mole. We got 0.06 moles. So 0.06 times 1,498 equals 89.9 kilojoules. Okay, it takes 89.9 kilojoules to break up that molecule. Okay, let's look at this side, water. Okay, the OH bond, 459 joules. We got 2 of them per molecule. So 459 times 2. 918 kilojoules per mole. Okay? But we don't got a mole. We got 0.1 moles. 0.1 times 918. Okay, that's easy math because 0.1 is 1/10 divided by 10. All you got to do is move the decimal place over 1. So this is 91.8 kilojoules to break that up. Okay, so this plus this $181.7 kilojoules. Okay, so that wasn't that bad. That really wasn't that bad. We know that to break all the bonds on the left side takes 125.9 kilojoules energy. Break all the bonds on the right side takes 181.7 kilojoules energy. So that basically tells us that the molecules on the right are harder to break, so they got stronger bonds, they're more stable. Okay, so the molecules on the right are more stable because they're harder to break. Okay, that makes sense. Stability is associated with kind of strength, I guess you could say. Okay, so basically what we have is the equivalent of something like this. Okay, we got a boulder in an unstable situation. This side's more unstable because it's easier to break, right? It's easier to break. That means it's got potential energy. Okay, because anytime something is unstable or it's easier to break, then that means it has the opportunity to break apart and reorganize into a more stable situation. For example, like a flimsy house, okay, it's unstable. If a big wind comes, then it's going to blow that house over. All that wood and materials is going to be much more stable just in a pile on the ground, right? Okay, it might not be as nice, you can't live in it, but it's technically more stable because it's flat on the ground. It can't break, it can't fall over. It can't fall over and make a big noise. It's already done that. It's already on the ground. Okay, so this situation, this side is unstable. It has potential energy. It has potential to go down the hill to a more stable situation. Okay, so these molecules have the potential to reorganize into a more stable, a stronger configuration. And in the process of doing that, they release energy. Okay, so this chemical reaction is in fact a combustion reaction. You have a hydrocarbon burning in the presence of oxygen to make carbon dioxide and water. That's your standard combustion reaction. And we know combustion releases energy. It takes a little bit of energy. Okay, you got to get this energy started. Once you provide the spark to light this combustion reaction, it's that once a few of these bonds break and reorganize into this, then the heat generated from that, of this, basically the analogy of the ball rolling down the hill to a more stable configuration, is going to create energy that's going to fuel the rest of this reaction. Because this is quite a bit of energy to break all this, but that energy is provided by the energy released through heat as it becomes more stable. Now, as a boulder rolls down the hill, it's going to release energy as sound and noise, right? Okay, but this combustion reaction is going to release that energy through heat and light. Okay, fire. All right, so I know I said a lot, and I'm hoping that you marinate on what I said, but the important thing to remember is that unstable equals potential energy, okay, because it has the potential to stabilize itself. Things always release energy when they become more stable. A ball rolling down the hill is going to release noise as it becomes stable and has low potential energy. Okay? So Another analogy is like, okay, when you got a pocket full of cash, okay, you had to go to work, just like this ball going up the hill. I could roll that ball up the hill by putting energy in, by putting in work. You can go work and you can make money, and your wallet will get fat, okay. But the more money you got in your pocket, the more tempted you are to go to the mall on a shopping spree, okay. So when you got all that money in the wallet, eventually you're gonna see something you like, and that's gonna provide that what we call activation energy to start the reaction. And you're gonna go to the mall and you're gonna buy that, and you see something else, and you're gonna spend that money, and then you're gonna be out of cash. You're gonna spend all that potential energy that was in your wallet, and then you're gonna go home and you can't afford to do nothing else. You're gonna go home and hang out on the couch, right? Okay. You're gonna be in a more stable situation because you don't have the potential to go spend all that money. Okay, maybe that ain't the best analogy, because being broke, a lot of people want to consider that being stable. Okay, they might consider that being unstable because you're stressed out because you ain't got any money to spend. All right, but whatever, marinate on that. All right.
All right, let's take a look at this part of the study guide. In nature, systems have a tendency to achieve instability or stability over time. Okay, everything has the tendency to end up in the most stable state. Okay, this might not be intuitive, but once again, just think of the boulder on the hill analogy. Okay, something that's unstable is teetering, and over time it's most likely gonna fall and eventually go to the more stable state, where falling to a lower level or something like that is not an option. All right, to make something less stable, energy must be added. Remember, this is less stable. To make something less stable, energy must be added. To get the ball up on the boulder up on the hill in a teetering position, it needs to be rolled up there, okay? Or it needs to be placed up there at some point. That takes some kind of energy. To make something more stable, energy is released, okay? As something goes to the more stable state, remember it loses potential energy. That energy is released. Instability is associated with high levels of potential energy, okay, because it has the potential to fall or release energy. In the combustion reaction that we just did, the hydrocarbon C2H6 burns in the presence of oxygen to make carbon dioxide and water. The products, carbon dioxide and water, are more stable. They're more stable than the reactants because oxygen is bonded to less electronegative elements, which means there is less of a struggle to share the electrons. If you got two or more electronegative elements bonded together, they're going to be struggling to hog those electrons. Okay, that's not exactly ideal. Okay, when oxygen bonds to hydrogen, it has a lot easier of a time hogging those electrons. This is why energy is released. Remember, the energy is released from this system, and when energy is released from a system, it's often felt as heat or observed as light. Okay, think of a fire. You can feel the heat and you can see the light coming off of it. We call that exothermic. Endothermic is when it takes in energy to become less stable. You know the energy was released based on our calculations, okay, because the bonds holding the products together are stronger, okay, and strong bonds make molecules more stable. Okay, to get this reaction started, a spark or some other type of ignition is required to provide the activation energy. Okay, the boulder doesn't fall over on its own. I mean, eventually, probably dirt and rock will erode away and the boulder will fall. But if you want that to happen right here, right now, you got to push it. Okay, you got to provide that activation energy. Even weak bonds require some amount of energy to break. Okay, even weak bonds require a little bit of energy to break. Okay, this is an important concept. Breaking bonds always requires energy. The forming of bonds releases energy because every bond that is formed happens to achieve some greater level of stability. This is analogous to giving a push to an unstable rock. Okay, it's just like giving a push to an unstable rock at the edge of a hill to get it to roll down the hill to stability. All right, hopefully this is starting to stick. Okay, let's do problem 2 on the study guide, looking at an acid. Okay, so we're looking at sulfuric acid. First thing it says to do is calculate the molar mass. Okay, so molar mass. Okay, so just like last time, we just add up the atomic mass of all of the elements on the periodic table that are in the molecule. And when you have 1 mole of this molecule, its atomic weight matches its weight in grams. So we got 2 hydrogens, 2 times 1 plus, we got 4 oxygens times 16 plus 32 for the sulfur. Okay, so we got 2 plus 64 plus 32 equals 98. Okay, so this is going to be it's 98 AMUs for 1 molecule, but when you have a whole mole of them, it's 98 grams. Okay, 98 grams, but we don't got 98 grams. That's the mass of 1 mole, but it says if 1 gram is added to a liter of water, okay, first off, how many moles of sulfuric acid is that? So how many moles is 1 gram? Okay. Okay, remember, it's just like a pizza. How many pizzas is 1 slice? If it's cut into 4 slices, it's 1/4. Okay, so this is 1/98. Okay, and if we do that division, it gives that you could technically write that. You could say 1/98 of a mole, but it's better to do it as a decimal. Okay, because it's just easier to type into a calculator when you're working with a decimal than a fraction. So 1 divided by 98 equals 0.01 moles. That's how many we got. Okay, that's how many we got here. Okay, how many actual molecules is that? This is a good question. How many actual molecules is that? Remember, 1 mole equals 6.022 times 10 to the 23. Okay, so if we got 0.01 moles, I know that the math is 0.01 times 6.022 times 10 to the 23. Okay, because this is basically, we have 1/98 of a mole, and if
1 mole is 6.022 times 10 to the 23, then we have this divided by 98, which is the same thing as doing times the decimal format, which is 0.01. Okay, so sorry I'm getting tired. I'm running out of analogies, guys. But let's do this math. Remember, when you're converting to molecules, you gotta multiply the amount of moles times how many molecules are in a mole. Okay, so just remember, this is how many molecules are in a mole. We have 0.01 moles. Okay, so which is 1/98. Okay, so it's basically, because if you look at it like this, 1/98 is, so this is 6.022 times 10 to the 23rd divided by 98, basically. Okay, which you could also write that as 6.022 times 10 to the 23rd times 1 divided by 98. Okay, that's the same thing. 6.022 times 1 divided by 98 is the same thing as 6.022 times 10 to the 23 divided by 98. Okay, so which is the same thing as writing it as 6.022 times 0.01. Okay, because 1 divided by 98 is 0.01. All right, so 6.022 e to the 23 equals times 0.01. Okay, equals 6.022 times 10 to the 21 molecules. Okay, which makes sense because this is basically 1 moving the decimal place 2 to the left, and 21 is 2 zeros to the left of 23. Okay, so that makes sense. Okay, so that's how many molecules we got. All right, it's a lot. Okay, it's a lot. That's how many molecules that is. So the question is, how many hydrogens are released? How many hydrogens are released? So for every one of these molecules, how many hydrogens is released? Well, both of these hydrogens are going to be released because that's what an acid does. Okay, an acid releases a hydrogen. Okay, and when it does, it leaves the electrons behind, and then the positive hydrogen goes off into the water and makes the water positive, or makes it more acidic. Okay, so both of these hydrogens are going to go, because this is such an electron deficient molecule, because you have all these very electronegative elements trying to share their electrons, and when they're added to water, they're just gonna kick those hydrogens loose, okay? Because that means less sharing, right? And then those positive hydrogens are gonna go off, and they're gonna bond to the water. They're gonna go over here, and they're gonna bond onto that lone pair of electrons on the water and make that water positive, okay? So if both of those hydrogens leave, then that's just 2 hydrogens for each of the molecules, and there's this many molecules, so we just do 2 times 6.022 times 10 to the 21, which I believe is gonna be 1.244 times 10 to the 22nd, because when you multiply 6 times 2, it goes into 12, so that adds another decimal place. Let me check on the calculator just to make sense. 2 times 6.022 times 10 to the 21 equals Oh, it's actually 1.2044. Okay, there you go. 1.2044. So you could just round this to 1.2 times 10 to the 22. All right, good. There's all your stuff about the acid question.
All right, let's take a look at this last part. Okay, there's different options that'll work for this, but I think the best is kind of what I'm gonna give right now. So, an acid makes water more acidic. Okay, when you add acid to a water, that water becomes more acidic, but a base will make the water more basic. Acids and bases affect the charge of the water. Okay, water can be charged, and acids and bases affect the charge of the water. When water is acidic, the water is more positively charged. Okay. When water is more basic, the water is more negatively charged. This is because acids release the acids release a hydrogen ion into the water, which has a positive charge. Okay, because when the acid molecules release the hydrogen, it's because they're already strained, struggling to share electrons, and they don't want to share. They want to hog the electrons, and when they're added to water, the hydrogens have the opportunity to leave, or I guess more so the acids have the opportunity to kick the hydrogens out, because the hydrogens are able to go and bond to the lone pair on the water. And acids pull, bases pull hydrogen ions off of the water. Okay, so a base will pull a hydrogen off of the water, and that leaves the water negative. Okay, so just a reminder. Water has these two lone pairs. Okay, the free hydrogen can hook onto the water right there. Okay, and when it does that, makes the water more positive. Okay, but a base has a lone pair on it, and the base can pull one of those hydrogens off of the water, and that makes the water negative. Okay, because when water loses a hydrogen, it becomes negative, and that leaves the base pulls hydrogen off the water, leaving the water negative. If both an acid and a base are added, the base will accept the hydrogen ion from the acid, the base will accept the hydrogen ion from the acid so that it doesn't bond to the water, and the water will stay neutral. The water will stay neutral, okay? When water is acidic, it has a pH less than 7, okay? It has a pH less than 7. But when water is basic, it has a pH more than 7, okay? Low pH is acidic, high pH is basic. When the water has a pH of 7, it is considered neutral, all right? Typically, water is neutral. Okay, I want to give you a reminder on how to do the scientific notation on the calculator. Okay, what I find is the best way is to use this this E button right here. If you look above the normal key symbol above, there's like a purple symbol on all the keys that can be accessed by hitting this second button. Okay, so if we type in 6.022 second E23, that's the fastest way to do scientific notation. Okay, another way you can do it is by, if you use this way, I'd always recommend using parentheses. 6.022 times 10 raised to the 23rd. Okay, that's another way that it can be done. It's just a few more buttons, more chance to make error. One other thing I want to show you is the store button. When you're using the same number repeatedly, such as the number for moles, I would recommend just going 6.022 second E23 and then hit this STO button. That's for store, and you can store it in one of these, any of these variables. And just, if you store it in A, hit, I already got it stored in A, but let's say store it in B, hit enter. Okay, now you can just hit memory and then access any number stored in these variables. Okay, so if you hit, so you can just hit select it and then hit enter, and then now you hit, it just equals. Okay, 6.022 times 10 to the 23 saves you a lot of time and chances for mistakes. So let's say we're gonna do some math. Let's say you got 2 moles. You want to know how many molecules that is? I got 2 moles multiplied by second, or I guess we don't gotta hit second, by memory B, and remember there's 6.022 times 10 to the 23 molecules in a mole. So if we got 2 moles, that's 2 times B equals, there you go. Okay, so that's a good tool. I recommend you guys use that. All right, that's gonna wrap this up. If you guys have any questions, just post them in the Google Classroom in the comments under this video, or come into class, ask me during class, or come into 9th block, or I'm also in there during lunch every day. Come by, feel free to ask me some questions before the test. Okay, good luck. Once again, the test will be for blocks 4 and 6 will be on Thursday. Okay, and then for block 1, the final exam will be on Friday. All right, good luck, guys.